Welcome to Trial Site News podcast series. Pallavi Tiwari joins us today. She is an assistant professor at the Department of Biomedical Engineering, Case Western University Research. So Pallavi, welcome.
Thank you. Thank you for having me.
The pleasure is ours. Now, first, Dr. Tiwari, we want to say it is an honor and a pleasure to have you on this show with us today. Trial Site News has a rapidly growing audience base, and our focus is to ensure that clinical research is more transparent and accessible so that more in our society can understand the critical research that progresses our healthcare collectively. Now, you have an incredibly impressive background going to top universities in both India and the United States. So could you share a little bit about your background and how you became interested in STEM?
Absolutely. So first of all, let me thank you for having me and thank you for the kind words. In terms of my background, I'm a biomedical engineer by training. I did my undergraduate degree in biomedical engineering in India. And then I moved to the United States for my master's and PhD at Rutgers University. Since then, I've been an assistant professor in biomedical engineering at Case Western Reserve University. So in terms of, how I got interested in STEM, it probably goes way back when I was little. So my parents tell me that I used to, enjoy tinkering with things, and I was always good in STEM related subjects. In fact, one anecdote that I've heard from my parents tell people multiple times is I used to enjoy going to school to an extent where I would cry over weekends since there was no school. So, that's how I grew up. And so in high school, I realized that I wanted to be an engineer. What kind? I had no idea. So when it was time to choose a major, I reached out to my dad's friend who happened to be a professor in an engineering school in India. So when I met with him, the first question he asked me was, what would you do? What would you want to accomplish with your engineering degree? And that got me thinking. That's when I realized that I wanted to get a degree in a field that allows me to make a difference in people's lives. And he recommended that I join biomedical engineering. And I'm glad that he suggested that, and I ended up doing it because here I am 20 years later, still loving every day of learning what biomedical engineering has to offer in healthcare, and delighted to be a part of it and to be able to make a small contribution of my own in this field.
Which is special, and not everyone gets to do what they love. It sounds like this is something that you thoroughly enjoy doing, so that's a special place to be. So what words then of advice or encouragement do you have for other young researchers that are just getting started?
Well, as cliche as it sounds, my advice would be to persevere. The reason why I'm saying that is because as scientists, we face a lot more failures than successes. To give you an example, our experiments on a day-to-day basis don't often work out. Our hypotheses fail, papers and grants get rejected, and very often when these things translate over to clinical trials, they're inconclusive. And this is especially true for the field of oncology, since we're dealing with such a tough disease. So it's important to keep in mind that, in the big scheme of things, you got to keep persevering and keep looking at what the end goal is, which is to help move the needle forward towards improving healthcare. Having said that, it's also, I would also want to mention that research is a very rewarding experience, personally for me, at least. For every big win that you have, you tend to forget all the failures that you've left behind. And, we often, when there is a failure in front of us, we tend to forget the big picture. So my advice would be to just continue to persevere. And in that moment when, things are not going your way, it may not really seem like it's worth it, but eventually it all comes together and it really is worth it.
Sound advice. So what made you pick Rutgers for your graduate work?
So when I had to choose my graduate school, I knew that I wanted to work in this field of machine learning and computational modeling for cancer applications. And that's how I found my PhD mentor, who was back then an assistant professor at Rutgers University. And he was doing some very interesting work on using machine learning for prostate cancer applications. I joined Rutgers University, and my PhD thesis was on developing computational models for prostate cancer grading. I've known my PhD mentor for over 14 years now.
Oh, wow.
First as my PhD advisor, and now he also is my colleague at Case Western Reserve University. And together we continue to collaborate on many different projects in multiple different applications in oncology.
So you mentioned the guidance you got in not just the overall engineering, but picking something specifically. What got you interested in particular in picking the specialty that you have today?
Well, honestly, when I got into biomedical engineering, or 15 years ago when I first got introduced to this field, I had very little understanding of how machine learning algorithms actually work. So over the course of time during my undergraduate degree, I learned about these computation models that seemed like they had huge potential in identifying patterns or learning patterns in an image that even experts couldn't recognize or couldn't discern. So this got me intrigued and fascinated by this idea of using computational models for various different applications, especially for disease characterization. And back in my undergraduate days, with little supervision, my friend and I developed a software navigation system to help visually impaired people navigate within an indoor environment. So this whole process of identifying a clinically important problem and developing a functional prototype in order to solve that problem was really what got me interested in the field of computational analysis, and had me and so that's how I considered getting into doing research in this space.
So let's change gears a little bit here. Your specific focus is highly complex and technical. Could you share how your current project unfolded?
Sure. So as I mentioned, my PhD work was on computational modeling in prostate cancer grading.
Yes.
And so what happened was, towards the end of my PhD, my advisor introduced me to a neurosurgeon at Rutgers University who explained to me the challenges that he faces on a daily basis with brain tumors. And it seemed to me that unlike some of the other cancers, including prostate cancer, brain tumors, and especially glioblastoma, which is one of the most aggressive brain tumors, the treatment options happen to be quite limited. And that's when I realized that computational modeling can play a huge role in addressing some of these challenges that neuro-oncologists and neurosurgeons face when they deal with such a complex problem, as glioblastoma, or as aggressive as some of the other brain tumors. So towards the end of my PhD, I got started. So I started working in brain tumors towards the end of my PhD, and started having conversations with neuro-oncologists, neuroradiologists, and neurosurgeons. And during my conversations, we very quickly realized that one of the biggest problems in neuro-oncology is to distinguish benign radiation effects. So these are essentially benign side effects of this aggressive chemoradiation dose that brain tumor patients get, from tumor recurrence, which is cancer coming back. And the reason why it's important to distinguish these two conditions is because if the patient has cancer recurrence, then you want to be able to identify it quickly so the patient can be treated. But if they have a benign radiation effect, then there are treatments that are much less aggressive. Sometimes it's just wait and watch, and the treatment effect would go away. So it's important to recognize these two conditions. Now, the challenge is that these two conditions look very similar to each other on routinely acquired MRI scans. And in the absence of a reliable, non-invasive way to distinguish them, the only definitive diagnosis comes from surgical intervention, which, as you can imagine, for a patient that has a benign condition, this would mean that the surgeon would go in and cut open the skull and either take a biopsy specimen or scoop out the entire lesion, which was completely unnecessary. So over the course of last 5 to 6 years, as we've started to work on this problem, we have been working on developing machine learning and computational imaging methods to non-invasively distinguish these benign radiation effects from tumor recurrence. And one of the huge or unique advantages of the techniques that we develop is that they are based on routinely acquired MRI scans. So you don't need to go and get fancy imaging or expensive imaging like PET or spectroscopy or perfusion. All you need to do is, get a routine MRI scan that is part of current clinical care, and we extract information using our computational models from this routine MRI scan to be able to identify if a patient has a benign condition or if they have tumor recurrence. So that's the first part of the project, right? Mm-hmm. There's another aspect to all of this. So the first part is to distinguish these benign conditions from tumor recurrence. And the second aspect of the project is for targeting biopsies. Now, this would be important in patients that need to absolutely get a surgical biopsy, surgical intervention for disease diagnosis. And there, the idea would be to use these computational models as a GPS navigation map for the surgeons to go in and figure out where to take the biopsy specimen from. And this whole idea of doing these, creating these GPS navigation maps really occurred to us during our conversation with one of our collaborating neurosurgeons at Cleveland Clinic. And he was telling us the challenges that he faces right now, because there's really no way for him to tell whether a specific region where he's taking the biopsy from, is it truly tumor recurrence or is it a treatment induced a side effect, which is essentially tissue damage. And if he misses that location of where the biopsy is taken from, the diagnosis could be completely wrong. And so that's where we sort of got into this idea of creating a GPS navigation map for helping neurosurgeons figure out where to take the biopsies from.
I see. Now, from what our research shows, you're involved in developing a GPS map to guide devices with 90% accuracy in pinpointing brain tumors. We know this is part of a movement towards a more precise approach to targeting cancers. Could you describe the current challenges in these procedures and how your research will help us get to a more precise outcome?
Sure. So one of the biggest challenges with the current clinical standard of care is that these post-treated lesions in brain tumors, they tend to be highly heterogeneous. What that means is that in the same lesion, you could have tumor recurrence and you could have this tissue damage because of the treatment that these patients are getting. And when a neurosurgeon goes in, they only get one shot at doing the biopsy. So there's only one location. In most cases, there's just one location that they could target to get that biopsy specimen. The other challenge is, of course, we're talking about the brain, which is a very sensitive organ. So neurosurgeons have to be very precise when they go in and take the biopsy sample. So what we have been working on is to help them do this whole procedure of targeting biopsies in a sort of more refined way. And so what I mean by refined is we provide the objective would be to provide them with a sort of a navigation map where they can go in and know precisely where tumor recurrence is going to be with high accuracy. And the way we do that is we create a heat map. And so if you can imagine, this is sort of like a weather map that you see on TV. And this heat map would mean that if there are red regions, red hotspots, those hotspots would correspond to where the tumor is. And the cold spots, which would be represented with, let's say, blue, would mean that those are the regions that are not tumor. So you should avoid those regions. So with that map, that color map that we provide to them, they have a better understanding of where they should go in and take the biopsy specimen from. And the end goal would really be to improve targeting of these biopsies as well as improving biopsy yield.
Right, which is a big deal. So, what was the genesis of this research initiative? What about funding?
So the research initiative started in 2013, right
Mhm.
after I graduated from my PhD and started working in brain tumors at Case Western Reserve University. And during that time, we started to build collaborations with different clinical institutions. And the first collaboration we had was right in our own backyard with University Hospitals and Cleveland Clinic. And then during the course of time, we've built several collaborations with multiple different institutions, both in the US as well as internationally. And in terms of funding, in 2014, I received my first pilot award from my own university to start working on this problem. And as we worked on this problem, it started to give us very promising results. So, one number that you mentioned, we're close to 90% accurate in distinguishing these benign radiation effects in tumor recurrence.
Yes.
The other finding that we had during the course of this time was we did this very interesting human machine comparison study where what we did was we had the results that we got from our computational models. And in parallel, we compared these results with two neuroradiologists who were given access to the same imaging scans. And so, what we found in that comparison was that our models were twice more accurate than these experts in identifying these radiation effects in tumor recurrence. The addition to that finding since then, what we've realized is the real value is not necessarily to compare these two, but to really bring the best of both worlds, in that you bring the machine with the expert and see how well these two work together in identifying such challenging problems like distinguishing these benign conditions from tumor recurrence. So as we've started to do that, as we've started to think about this problem more as working together and joining forces with the human and the machine, we've started to see some very compelling results. And we've also started to see a lot of interest from the community to not only help build these tools, but also to use these tools in their clinical practice. So, we've been fortunate to get funded through the state of Ohio, Department of Defense, Dana Foundation, and more recently, we got awarded the V Foundation Translational Award, which will essentially allow us to translate some of this work into the clinical trial, which will likely happen in 2021.
Well, congratulations.
Thank you.
Now, the original research was done via a retrospective study, reviewing the cases in which the investigators knew the outcome. And now you must validate the research in clinical trials. However, before that starts, you will, in the interim, you have a little bit more work to do in optimizing the computational algorithms. Can you break this down a little more for laypersons? What do you have left to do before you can proceed to clinical trials?
Sure, that's a very good question. So, I've been talking about this 90% accuracy that we've obtained on our retrospective cohort. And that sounds great. It sounds very appealing given how challenging this problem is. However, as we start to talk about moving this technology into clinical trials, these values actually start to hold a lot more meaning, right? So this 90% accuracy will 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 have a specific meaning when we talk about it in terms of clinical trials. So what we are working on right now is to optimize our machine learning models such that we can maximize the sensitivity of diagnosis of tumor recurrence. You want to minimize misclassification of a patient that has tumor recurrence. So instead of worrying about the accuracy, what we are focusing now is to maximize our sensitivity of diagnosis of tumor recurrence in these patients.
So, you were working to conduct clinical trials by 2021 or early 2022. So, this will involve Case Western and the Cleveland clinical team as collaborating as sponsors and investigators. Is this correct?
Yes. So, we have a very collaborative clinical team at Cleveland Clinic. And the idea is that we will develop these algorithms, these computational models at Case Western, and rigorously evaluate these models on retrospective cohort. And in 2021, the goal would be to translate this technology into their navigation system at the clinic, so we can start to do these clinical trials in patients starting 2021.
So will you need to raise funds for the clinical trial? Will the research investigators fund the study?
Well, like I said, we've been fortunate in terms of getting funded to get this started. So we recently received a V Foundation Translational Award. Uh, Part of that award will initially fund doing the retrospective analysis and optimizing our models in terms of improving our sensitivity and specificity, and the part of the fund will allow us to do the clinical trial, and this will be in collaboration with Cleveland Clinic.
Right. So once the algorithms are optimized and the clinical trials commence, what is an optimal outlook for how your research will transform care?
That's a great question. And so I'll answer that question with pointing out two different aspects of these algorithms that we need to optimize for and we need to understand.
Sounds good.
The first aspect is the treatment related toxicity, and the second aspect is financial toxicity. So, when we talk about treatment related toxicity, we're talking about these patients that have glioblastoma, right? So, glioblastoma patients have very limited survival. The median survival in glioblastoma is 15 months. So, given this, the challenges with their survival, you want to not only maximize their survival times, you also want to maximize their quality of life. And if you think about doing surgical resection, surgical intervention in patients that have a benign condition and have already undergone highly aggressive treatments, it's just the thought of it is it's scary. So what our goal is if there is a surgical intervention that has to happen in these patients, it needs to be optimized. It needs to minimize the errors that are associated with the surgical interventions. What that would mean is every surgical intervention will then be worth its time, right? So not only in terms of money, but also in terms of where in terms of misdiagnosis. You don't want to miss any patient that has tumor recurrence as being misdiagnosed as having a benign condition, and optimize patients that don't need that surgical intervention at all. So that's the treatment related toxicity. The second aspect is financial toxicity. So we're talking about a treatment that costs $30,000 to $50,000 at the very minimum. That's a lot of money. And so what we want to make sure is that these surgical interventions are, for every surgical intervention that happens, you are getting its worth by both in terms of getting the right diagnosis as well as making sure that you don't have to do another surgical intervention to get the right diagnosis.
Well, let me rephrase that question one more time. So how were you and your team able to figure out what biomarkers to focus on that make the difference?
Sure. So what I'd like to think is the approaches that we build using machine learning are slightly different and in some sense unique than some of the other works in this space. And what I mean by that is, when we think about machine learning, people tend to think of this black box where you don't know what goes in, you don't know what comes out. It just gives you a decision of yes or no, let's say, right? Mm-hmm. In contrast, what we have attempted to do over the course of our research is develop solutions or develop biomarkers that also provide some biological intuition. The reason why this is important is because when our clinical end users are using these tools, they need to have an understanding and appreciation of what goes into the model so they can be involved in it and they can understand the output of the machine learning model. So to give you an example, a couple of years ago, we developed an image-based biomarker that we call collage. And the idea behind collage was that we know when we talk about cancer, especially glioblastoma, which is a highly heterogeneous condition, a highly aggressive tumor. We know that the microenvironment is very chaotic. It's, tumor cells growing in all directions. So in order to compute this complex microenvironment, we use a concept from high school math called entropy. Now, entropy is a measure of disorder. And so the idea is that if you were to compute these entropic measurements from this highly chaotic tumor, then you would get high entropy values as compared to patients that have a benign condition, or let's say they have a benign radiation effect. So what we observed during the course of our research was that patients who tended to have highly aggressive tumor tended to have higher entropy values obtained from their imaging scans compared to patients that had a benign condition. Now, this concept of building this biomarker in terms of these mathematical numbers and capturing this concept of entropy is something that our clinical collaborators appreciate, and that's why it's they've been open to the idea of adopting them in clinical practice, and that's how we sort of move towards incorporating these biomarkers into a clinical trial.
One of the hopeful elements of this is that the new technology will not only hopefully save patient lives, but also saves them money. Can you explain the average costs and how this can possibly save patients money?
Yeah. So, like I mentioned, sorry, let me say that again.
Yeah.
So the surgical interventions in brain tumors, especially in United States, tend to be very expensive, and the costs are in the range of $30,000 to $50,000 on average. So what we hope to accomplish with this project is essentially twofold. First is we want to be able to non-invasively identify patients who have a benign condition and potentially avoid this $50,000 treatment, which is not only highly invasive but is absolutely unnecessary. And the second aspect is where patients do need a surgical intervention, where it's absolutely necessary to get a surgical intervention for disease diagnosis. We ensure that the money is well spent by providing a reliable diagnosis of the disease. So that's how we hope to save our patients money as well as give them the optimal diagnosis for their disease.
So finally then, do you see this technology getting commercialized? Will the university license the technology to a partner for commercialization?
Absolutely. That's another great question. So we have in the past been funded through various translational mechanisms to start to think about moving this technology towards commercialization. So in the start, we were funded through the Case Coulter Translational Award. And more recently, we were funded through the Ohio Third Frontier Mechanism to build a prototype for our GPS navigation map. And again, this V Foundation award that we recently got is allowed us with an opportunity to move this technology into clinical practice. Now, in terms of commercialization, we could certainly, we're currently exploring options in terms of our licensing possibilities. One possibility could certainly be to partner with an OEM, and that's something that we are still considering and we are still figuring out as we go along building this technology forward.
Well, thank you for taking the time to join us today, Dr. Tiwari. It's been an illuminating experience.
Thank you so much for having me.